Hello, it's the crazy calculus nerd, Kitty Morgan here. And I'd like to take a look at one of probably the toughest optimization problems I have ever seen. And it's because you have to really, really think about this one hard. It's not as nice as, well, here's a formula and here's something and I'm just going to plug it in. This is a pretty tough one. So I wanted to have a talk with you about this. And this may not be something that brand new teachers do, but it might be something that veteran teachers or teachers who have kids in BC might want to try, because this is very challenging. All right, so let's look at our problem. It is really a true AP problem from 1994. This is a BC4 problem. And we have a parabola that is limited between 0 and root 6, and we want to find, and we have a line tangent to the graph at a point that actually hits the parabola. So I'm not going to do part A. I'm going straight to part B. And so part B says, for what value of W is there a minimum? So AW is the area of the triangle, so we're trying to minimize the area of a triangle. So first of all, I'm going to write that thing I'm trying to maximize or minimize, and that is the area of a triangle. So now let me see if I can't visualize what the triangle they're talking about is. It says that AW is the area of the triangle formed with the coordinate axis and the line tangent. So here's my line tangent, and so I like this, and where it meets this coordinate axis. This visual is very important to get before we start this. All right. So that's the triangle that I'm trying to maximize or minimize. And so I've got to think, okay, so what is the base of this triangle? Well, the base of this triangle is the length from 0 to where this line hits the x-axis. So really, and I need to write this in words for me, the base of the triangle is really the x-intercept of that tangent line. So if I could figure out what the x-intercept is, then that length from 0 to that would be the base of my triangle. The height of my triangle is going to be where the tangent line crosses the y-axis. So the y-intercept of the tangent line. So because my base and my height are parts of this tangent line, it might make sense for me to find the equation of the tangent line. So I'm going to go up here and work with that. So y minus, and the y value, I need a point. So I'm going to choose the point of tangency. Okay, so that's my y value. Equals, I'm going to come back to the slope in just a minute. X minus, this x part of the point is w. Okay? Now, I need to find the slope of this tangent line, and we know that the slope of the tangent line is the derivative. So I'm going to take the derivative of my function. Let me do f. That's what turns this in, excuse me. So f prime of x is equal to negative 2x. We don't want it at any point. We want it at this point of tangency. So I really want the slope at w. Go. So now we have the equation of the tangent line, and let me round. So this is the equation of the tangent line. At w6 minus w squared. Now, we've said that the things that we're looking for, now notice in an optimization problem, you always write down the thing you're trying to optimize, and then you go do a whole bunch of other work just to get that thing in terms of one variable. So this is a whole bunch of other work that we have to do in order to actually do this problem. So eventually I'm going to come back to this. So if you want to find the x-intercept of any line, don't you let y equal 0? So we're going to do that. We're going to let y equal 0 and solve for x for this tangent line. So if y is 0, that yields 0 minus, and I'm going to keep these in parentheses, and it'll make sense a little bit maybe. And then I'm going to do, I'm going to actually distribute this, and maybe this will make sense when you see some other things, but I think it makes it easier. And that's going to be negative, negative, which makes plus 2w squared. And so that's we're going to solve for x. So that's minus 6 minus w squared, and minus 2w squared, and then equals negative 2wx. So if you divide by negative 2w, that's going to be 6 minus w squared minus 2, plus, there we go. Sorry about that. Over 2w, and that's going to be equal to x. All right, so that whole thing is the x-intercept. So now I'm starting to write the thing that I'm trying to maximize or minimize, in this case minimize, in terms of one variable. And I know I'm keeping all this whole, but there might be a reason. I might break it down later. You never know about me. Okay. So now I must find the y-intercept. And to find the y-intercept, you let x be equal to 0. You know what, I'm going to do this in a different color so we can differentiate these. So let x equal 0. And when you let x equal 0, you get y minus 6 minus w squared equals negative 2w times negative w. Because you put 0 in for x. So now we have y equals, and you have negative times a negative, so you have 2w squared plus 6 minus w squared. All right, so that's what we're going to put right there. We're going to put 2w squared plus 6 minus w squared. I don't know if you know now why I chose to use this craziness, but it's going to clean up very nicely. So now let's kind of put this together. We're going to actually use our calculator to find the root of a derivative and all of that. So you can do this by hand, but I do not do this by hand. So I'm going to, let's notice that this is the same thing. So really I have 2w squared plus 6 minus w squared all squared. And then I have 1/2 times 2w, which is 4w. This is just going to be easier to put in your calculator than it is not. And you can square all this out and do all this by hand. I'm just not going to do it. So this is a calculator problem for me. So I'd like to know where the derivative is equal to 0. So I'm going to pause right now and pull up my calculator.